Hello everyone, in this video we are going to look at a CSTR and look at a first order reaction, try to solve the kinetics for that. So a CSTR is a continuous stirred tank reactor. And so what this means is it is continuous, so we have some continuous flow in and out of the reactor. We have a molar flow rate of our reactant species A coming into the reactor on the left, and then we have some flow rate of the final products and the final reactant A coming out of this reactor. It is stirred, which means there's this propeller down here which is mixing the whole reactor. So this whole reactor is well mixed. The concentrations of all the species are uniform throughout this reactor. And it is also a tank, and it is also a reactor because we have a reaction happening here. In this problem, we're going to assume an isothermal reaction, so a constant temperature for our species here. We're also going to assume this is a liquid phase reaction, and that will imply that this is going to be a constant volume reaction as well, because liquid phase reactions typically don't change volume too much during the course of the reaction. And this problem is a reactor sizing problem, which basically means how big should this reactor be? So what should our volume of the reactor be in order to reach certain conversion from A to B in this reactor? We're going to solve for our conversion X as a function of our volume of the reactor V, as well as our flow rate, little v. This is our volumetric flow rate that we have coming into the reactor and coming out of the reactor right here. First, we're going to start with a mole balance. So that's going to be dN dt. And let's look at this in terms of our reactant A. So dNA, number of moles of A as a function of T. And this is going to be equal to how much comes into the reactor minus how much leaves the reactor plus whatever is reacted in the reactor. So we're going to call this generation, and that's basically our reaction term. This will be negative for our species A because it's being consumed in this reactor. So first off, our in is going to be equal to FA naught. This is our molar flow rate of A coming into the reactor. So I'll label this on our diagram over here. And this is equal to concentration of A in the inlet times our flow rate into the reactor. Our out term is going to be equal to FA. So I'll put this on here as well. And FA, we're labeling this as FA and not like FA outlet or FA end, because what comes out of the reactor is at the same concentration as all of the species within the reactor. So we're imagining for this assumption, since we have a CSTR, is that there's going to be some initial concentration and initial flow rate, FA0, but once it reaches inside the reactor, now all of the concentration of A is at its ending concentration, so Ca. So again, this is going to be equal to Ca times V naught similarly. And our generation term is going to be equal to our rate of reaction, Ra, times the volume of our reactor. Now, the nice thing about working with a CSTR is that we can actually set our dNA dt equal to 0 because this is operated at steady state. So now we can basically solve this equation right here. So we can set in is equal to FA0 minus out, which is equal to FA, plus RA times V, and this is all equal to 0. Typically, we solve this equation for V. We're basically asking the question, to reach a certain conversion or a certain difference between FA and FA naught, how big of a volume of a reactor do you need? So let's solve for V right here. So we end up with V is equal to FA minus FA naught divided by RA. And usually the way we write this, since FA naught is going to be bigger than FA, I'm going to rewrite this as FA naught minus FA divided by negative rate of reaction of A. And this also makes sense because this rate of reaction term is going to be negative, so these two negatives will cancel out when we plug in for our rate of reaction. Another way to do this is to write this in terms of concentration, so that becomes Ca naught times little v naught, our volumetric flow rate, minus Ca times little v naught divided by, again, minus RA. So we can look at this both in terms of concentrations or molar flow rates for this problem. This equation down here for V is known as the design equation for CSTR. So this is a good starting point whenever you see a CSTR problem. You can jump right here to this equation. We also like to write this in terms of conversion. So the conversion X is defined as the number of moles of A that have been reacted divided by number of moles A fed to the reactor. So first off, the denominator here, number of moles fed to the reactor, is just going to be equal to FA naught. So that's our molar flow rate of A entering the reactor. Number of moles reacted is not just equal to FA, because FA is basically what you have afterwards after A has reacted. So in this case, it's actually equal to FA naught minus FA. This is all of the stuff that has been converted inside of the reactor. So our X is equal to FA naught minus FA divided by FA naught. And one way to write this, we want to solve for FA, so we can plug in right here to this equation. We can rewrite this as FA is equal to FA naught times 1 minus X. And in terms of concentrations, we can do a similar trick. Here we can divide by our total volume, and we can also write this as CA is equal to CA naught times 1 minus X. And we can substitute in FA right here for FA in this equation for V. So we end up with V is equal to FA naught minus FA naught 1 minus X divided by our negative rate of reaction. And we can simplify this a little bit by multiplying through by this term FA naught here. So we get FA naught minus FA naught plus FA naught times X divided by negative RA. And here we can get these two terms cancel out, so we end up with FA naught times X over minus RA. And while we're here, let's also write this in terms of concentrations. That's going to be CA naught times little v naught times X divided by minus RA. So we have two different ways of looking at this problem. Now the next step is to plug in for RA. So this depends on which type of reaction, which type of problem you're solving. In this case, we are going to set up an equation for RA as a first order reaction. So RA is going to be equal to negative K times the concentration of A. And if we plug that in here, now first I'm going to rewrite this in terms of conversion. So again, conversion, we had this expression, CA is equal to CA naught times 1 minus X. So I'm going to plug that in here. We get RA is equal to negative K CA naught 1 minus X. And now we can plug this in to this equation for V, and I'm going to use this concentration equation because we already have a CA naught and those two will cancel out. So we end up with V is equal to CA naught little v naught times X over K CA naught 1 minus X. And here we can cancel out these CA naughts. So we end up with V naught X over K 1 minus X. This is one way of looking at the problem where we've solved for the volume of the reactor as a function of conversion. We can also solve in the opposite direction where we solve for conversion in terms of our volume. So let's look at that problem as well. If we move all the constants over to one side of the equation, we get big V over little v times K is equal to this fraction, X over 1 minus X. And now if we solve this for X, now I wrote this solution for X in this format because we have a couple things that we can substitute in to solve for X. So first we have this quantity V over V naught. This is known as the space-time tau. So think about these units here. The units of volume is going to be some unit of volume, let's call it liters. And the volumetric flow rate here is going to be liters per second. So the units of tau is going to be liters divided by liters per second, which is in a units of time. So this is our space-time. One way to think about space-time is it is the mean residence time of some amount of fluid as it passes through the reactor. So typically, as some of this volume is entering the reactor, how long does it last inside of this reactor? And now we can simplify this equation a little bit so it looks a little nicer. Now we have tau times k over 1 plus tau k. And we can do one more step. We can think about what this tau k represents. If you notice, x here is dimensionless. And this quantity tau k is also dimensionless. You'll notice tau has units of time because it's our space-time, and k, our rate constant, has units of inverse time. So together they are dimensionless. And it turns out this quantity tau k is equal to the Domkohler number for a first-order reaction. The Domkohler number is actually defined as minus Ri naught V divided by Fa naught. And since our reaction rate might change depending on if it's a first order reaction or second order reaction, this will be a different quantity for different orders of reaction. So this tau k is not going to be what it is for a second order reaction. In our case, it's going to be equal to kCa, which is our first rate of reaction at the inlet, divided by Ca naught times V naught, which is our flow rate at the inlet. These two terms cancel out. And again, remember this V over V naught is our space-time, so we get K times tau, which fills into this quantity right up here. So that's our Domkohler number for this problem. And we can think of the Domkohler number as the rate of reaction at the inlet divided by the rate of convection at the inlet. So for high Domkohler numbers, we would expect we're going to have a lot of reaction taking place. For lower Domkohler numbers, we're thinking the rate of fluid flow through the reactor is going so fast that it doesn't have enough time to react. And so we'll get to lower conversions. So if we write our previous expression for x, which we had already solved, in terms of the Domkohler number, we get Domkohler number divided by 1 plus the Domkohler number. So the Domkohler number, remember, is equal to our volume over our volumetric flow rate. So this is our tau times k. So I'll rewrite it in these two different ways. So this can basically tell us that if we wanted to achieve a high conversion, we want a high value of the Domkohler number. And we can achieve that by either using a large space-time, so large volume reactor, or a small value of our volumetric flow rate. And we can also see if there's any way we can change our rate of reaction, maybe by increasing the temperature or by changing some of the chemistry, maybe using a catalyst, then that can also lead to higher levels of conversion. To summarize, in this problem, we had a CSTR with a first order reaction, and we assumed this was an isothermal liquid phase reactor. We found the conversion as in terms of our volume and volumetric flow rate, and we also wrote it in terms of the Domkohler number. If you want to test your understanding, try solving this problem again, but with a second order rate reaction. So let's say that our rate of reaction is equal to minus k Ca squared. How would you solve the problem? How would it change? I'll give you a hint. It will get a little bit more difficult. You'll have to solve a quadratic equation to find your conversion, but you can still write this conversion in terms of the Domkohler number. But again, remember, since this is a second order reaction, this will be a different version of the Domkohler number. I hope you enjoyed this video. Thanks for watching.